Hi, everybody. So then in this video, we're going to talk about diagonalization. It's, at least for now, the main reason we're actually talking about similarity, because we want to know which matrices are similar to diagonal matrices, because diagonal matrices have a number of really nice properties. The biggest one is it's really easy to take a diagonal matrix to a power. All you do is take the power of all the entries on the main diagonal. So just so you see, to see what I mean, if you took the matrix 1, 0, 0, 2, and I took it to the third power, this is insanely easy because it's a diagonal matrix. It would be 1 cubed, 0, 0, 2 cubed. That's a result I gave before. So we want to know what kind of matrices are similar to those. Because if it's similar to a diagonal matrix, and if diagonal matrices are easy to take powers of, certainly it should be easy to take a power of the original matrix. And the answer is, it is. It's really easy. So let's go about talking about this process then. So diagonalization. A matrix that's n by n is called diagonalizable if it's similar to a diagonal matrix D. Now, you need at least an example. So then the matrix A here, it had these eigenspaces, one for the eigenvalue of 1 and one for the eigenvalue of 3. The eigenvalue space, the eigenspace E1 was spanned by 2 vectors, and the eigenspace E3 was spanned by 1 vector. These 3 vectors actually are linearly independent. Now, why do we know that? Because of a theorem we did before. If you remember, it's a theorem we did before, taking a bunch of vectors linearly independent in one space, a bunch of vectors in the other eigenspace. If these are separately linearly independent, when you put them together, they're automatically linearly independent. And here, that would then mean that you'd have 3 vectors from R3 that are linearly independent. So by the following R equivalence theorem, the great fundamental theorem of invertible matrices, that means that these 3 vectors are a basis for R3. So when you put them together, you have to get an invertible matrix. So let's do that. Let's take these 3 vectors, all eigenvectors, squish them together to make a matrix. We'll call that matrix P. So then notice that if you take P inverse times A times P and just do the multiplication, you get a diagonal matrix. I wonder if this can be done in general. And yeah, it is. That's actually the whole point of the next video. So then it shows then in this case that the matrix A is similar to a diagonal matrix. And the diagonal matrix, the entries on the main diagonal are the eigenvalues. That might just be why we were interested in eigenvalues and eigenvectors in the first place. It is. That's actually why. It's because this process right here, this is the thing that we had to have in order to go do lots of applications. We want to take powers of matrices, and to do so easily, we hope that our matrix is similar to a diagonal matrix. Okay, so then why do that? Let's just look at that process. For a moment, let's say that a matrix A is similar to a diagonal matrix. So you'd write, let's say A is then similar to a diagonal matrix. So that's a diagonal matrix, and it has entries on its main diagonal. I'll call them lambda 1, lambda 2, up to lambda n. That means then that there is a matrix P, so that P inverse times A times P is equal to D. Well, what I want you to do is to solve for A. So pre-multiply by P on both sides on the left. That will then give you A times P equals P times D. And then on the right, multiply by P inverse. That would then give you A equals P D times P inverse. Notice what happens. If you take A squared, this would then be P times D times P inverse times A again. So that would then be P times D times P inverse. But if you look on the inside, that's the identity. So the only thing left then is P times D, that's D squared, times P inverse. So then A cubed would then be A squared times A. A squared, though, is P times D squared times P inverse. And A is P times D times P inverse. But if you look on the inside, that's the identity matrix. So that is P times D squared times D. That's D cubed times P inverse. So if you continue this, this is called induction. Doing this as a form of proof would be called induction. If you take A to any integer power, the result is always P times D to the nth power times P inverse. And remember that D to an nth power, that's incredibly easy to do because all you do is you take the powers on the main diagonal. So this is really a product of three simple matrices. So if you want to take A to the 100th power, you actually only have to multiply three matrices together to do it. Neat, right? If you want to take A to the billionth power, you actually only have to multiply three matrices. That's really neat. That's really neat. So that's why we focus on diagonal matrices. It's because of that little algebraic trick. It's because a lot of our applications boil down to, I want to know what happens when this matrix is taken to a high power. Okay, enough of that. So what we need is some clever way to say that a matrix is diagonalizable. Now, I wouldn't go through this proof unless it was important. And in this case, it's important because it's a constructive proof. It means not only does it show you the condition that you need, but it provides for you the matrix P, and it provides for you the diagonal matrix. So this proof is useful just beyond just showing it's true, but to tell you how to form that similarity. So suppose A is an n by n matrix. Then A is diagonalizable if and only if A has n linearly independent eigenvectors. So in other words, if you have enough eigenvectors, then the matrix is diagonalizable. To show you why, I'm going to prove it really easy. It's not hard at all. So we'll go in one direction. Let's suppose that we have n linearly independent eigenvectors. We'll call them V1, V2 of the Vn. They all correspond to eigenvalues. What the eigenvalues are, we don't care. They could be equal, I don't care, but there's n of them, one for each eigenvector. Okay, so then I need you to form two matrices. So the matrix P is going to be the matrix that is just formed by looking at the eigenvectors, thinking of them as column vectors and putting them together to get one matrix P. We know that P has to be invertible because since the vectors V1 through Vn are independent, then by the great following equivalence theorem, the fundamental theorem of invertible matrices, that matrix P has to be invertible. And then define a diagonal matrix, which is lambda 1 times E1, lambda 2 times E2. It's just a diagonal matrix whose entries on the main diagonal are lambda 1, lambda 2, lambda 3 up to lambda n. Okay. Then notice that if you take A times P, you can do the matrix column multiplication to multiply A to every column of P. That would then give you A times V1, A times V2, A times up to Vn. But these are eigenvectors. So then A times V1 would have to be lambda 1 times V1. A times V2 would be lambda 2 times V2 and so on. Also, though, if you take P times D, you can do the same trick. Multiply P to each column of D. But the first column of D is lambda 1 times E1. So then you'd have lambda 1, take lambda 1 out, you'll then have P times E, and P times E1 is the first column of P. That's V1. So then the first column of P times D is lambda 1 V1. So if you want to look at the second column of P times D, the second column would then be P times lambda 2 times E2. Just take the lambda 1, the lambda 2 out and look at P times E2. But P times E2 is just the second column of P. That would then be V2. So the second column of P times D is lambda 2 times V2. I think it's obvious then that P times A times P is the same as P times D. And that means then there, since P is invertible, that P inverse times A times P is D. In other words, A is similar to a diagonal matrix. And what's really neat is the matrix that does the similarity is just a matrix of eigenvectors. And the diagonal matrix is the diagonal matrix with the corresponding eigenvalues in the exact same order on the main diagonal. So this is, as I said, an amazing result. This is the reason we actually were looking at eigenvalues and eigenvectors in the first place, is just to get to this. Now, reversing the argument's easy. It's literally just going back through these statements, just reverse them entirely. So it's not deep at all. I just want to show you how to use it really quickly. So then this matrix here, the matrix 1, 1, 0, 1 is not diagonalizable. It is not similar to a diagonal matrix. I write down the characteristic polynomial like we always do to get 1 minus lambda squared. The eigenvalue is only 1, and its eigenspace is the null space of A minus 1 times I. I just wrote lambda instead of 1. So then if you look at the null space of A minus I times x equals 0, you then find the solution space to the corresponding coefficient matrix time when it's equal to the 0 vector. By row reducing it, you can see the solutions is just spanned by the vector 1, 0. So E1 is spanned by the vector 1, 0. But 1 has an algebraic multiplicity of 2. That's all the eigenvalues. That's it. That's all the eigenvalues. There's only one eigenspace. But the eigenspace has only one linearly independent vector. I need 2. Remember, I need 2, the same size as the matrix. The matrix is a 2 by 2. So I need 2 linearly independent eigenvectors. And I can't. It's impossible. So this matrix is just not diagonalizable. It is not similar to a diagonal matrix. And I think that's enough for there. We'll then talk about how to figure out how a matrix is diagonalizable using different little sneaky tricks.